Welcome to our slide presentation today, and I'm Tom Irvine, and this will be a continuation of Earthquake Engineering Introduction. And since I made my last recording, I've gone and updated the slide package, so I'm going to go over a couple of the additions that I've made, and then we'll move on to our main topic, which is going to be historical earthquakes mostly. So back in the time of ancient Greece, then the belief was that Poseidon, well, the Romans called him Neptune, but we'll call him Poseidon, that triggered earthquakes by striking the ground or seabed with his trident. So there he is in his wrath and causing all that havoc and destruction. And then native cultures have had their own legends, and this is from the Pacific Northwest of the United States, up in the area of Washington State. And this is an art style that's kind of common up in that part of the world. And these indigenous people then believed there was this huge thunderbird, and this was a massive thunderbird that could come and actually grab a whale in its talons and then carry it up into the mountains and then drop it to the ground, and that caused earthquakes. And then the purpose of that was so that the thunderbird and its offspring then could eat the whale meat. So there's actually some kind of a historical background that goes along with this, that researchers believe this myth describes the massive 1700-year Cascadia subduction zone earthquake, approximately of magnitude 9.0. So this is the native people's interpretation, and then, of course, the dropping of the whale caused earthquakes, and also tsunamis was another effect. Pretty interesting to think about these cultures. So I can't remember if this was in the last package or not, but this is kind of an overview of what we're doing. So today we're still mostly on the sources of earthquakes. Well, we're actually going all the way up through structural damage, though, in this introduction. But yeah, it all starts with fault ruptures, and then there's the generation of seismic waves. And we've talked about P, the primary wave, and S for shear, or S can also stand for secondary. And both P and S are body waves. Then we have a pair of surface waves, which are Rayleigh and Love. And then that energy is going to cause ground motion. So we'll talk about peak ground acceleration and peak ground velocity and peak ground displacement, and also their time histories as well. And then that causes the excitation of our buildings, our bridges, our water towers, and so forth. And we will be talking about inertial forces, resonance, vibration modes a little bit today, and then even more so in future units. Then that can cause structural dynamics. So cracking can happen, for example. Columns can buckle. We'll talk about that, or have shear failures. We'll also talk about drift. So the story drift is an important concern, and connection failures and so forth. Now, there are different design standards that we're going to be talking about, and these will, for example, specify how much story drift is allowed. We'll talk about base isolation and damping systems as well, in terms of designs and codes and analysis and so forth. So earthquake engineering studies how seismic ground motion becomes structural damage, and how buildings can be designed to safely resist that excitation. Well, here's another new slide, and this is the Earth's natural frequency. So the Earth has a fundamental frequency of an extremely low number, 309.286 microhertz. And that's so low, it's more convenient to look at that in terms of the equivalent period, which is the inverse of the frequency, and that's about 54 minutes. Now, the mode shape is a spherical breathing mode where all points move radially outward and then back inward in phase. And there's always some microseismic activity of the Earth, but when we really see this mode excited is in the event of a major earthquake. So if the moment magnitude is greater than or equal to 8.5, then this mode can be detected readily by seismic stations all throughout the globe. That's for Lay and Wallace, their seismology textbook. And we've talked before about then the tectonic plate boundaries and how earthquakes tend to occur along these boundaries. But we're going to talk about an intraplate earthquake a little bit later today. It'll be the New Madrid earthquake that happened in the Mississippi River around Memphis, Tennessee, and the southeast corner of Missouri back in 1811 and 1812. So yes, these major earthquakes, 6.0 and above, tend to mostly occur on tectonic plate boundaries, but they could occur anywhere. And the reason you don't see a dot there for the New Madrid is because that was prior to 1900. In that slide, we've talked about the P waves, the longitudinal waves, the S waves, the shear waves. Those both are, again, body waves. Then we have our two surface waves, the seismic Love wave and the seismic Rayleigh wave. And the Rayleigh wave is really interesting. It's this rolling motion. And it's like an ocean wave coming into the beach, but ocean waves have prograde or clockwise motion of the water molecules. Whereas these Rayleigh waves, it's called retrograde or counterclockwise. We talked about that last time we met. Now, ideally, what happens is the particles then return to their rest position after the energy passes on through. Now, that assumes no permanent deformation, and we're neglecting things like Brownian motion. But idealistically, after the energy passes through, those particles of dirt or rock or granite, whatever they might be, go back to their rest position. We talked about tsunamis before, but we do have an addition. We have the equation then for the speed. Now this is called a shallow water wave speed equation, where the wave speed is the square root of the gravitational acceleration times the water depth. Now, as it turns out, tsunamis are a special case, so this equation will also work out in the deep sea. So it works for tsunamis because their wavelength is enormous compared to the ocean depth. So the ocean effectively behaves as a shallow water, even though it's miles deep, again for the special case of tsunami. So we talked before about how we have this displacement of these two plates that meet together in what's called a subduction zone. One plate going downward to the left, the other going upward and to the right, generating some longitudinal underwater waves, and those waveforms reach the surface, generate the tsunami, which in open sea then has a very fast speed, 835 kilometers per hour, but has a very low amplitude. And then as that waveform comes into the shoreline, then because h is decreasing, the speed c is decreasing dramatically, but there's also a very enormous increase in amplitude. You've all seen the videos of tsunamis reaching coastal areas and the destruction that's caused thereby. Okay, this is just a review. We talked about the different magnitude scales. There's several there, and M sub W, the moment magnitude, is the most commonly used nowadays. Just a few review slides there. We'll just kind of skip over these because we've seen these last time. Now, we've talked about this before, and this is going to become relevant again. And there's this children's song, "The Wise Man Built His House Upon the Rock," and another part of that song is "The Foolish Man Built His House Upon the Sand." And this was mostly in the context of when the rains came and the floods and so forth. But we can also apply the meaning of that song, the message, to earthquakes as well. So bedrock is considered one of the best conditions for earthquake resistance because it minimizes seismic wave amplification. It has high shear wave velocity and stiffness, which result in low strain amplification. Okay, we talked before about how we're going to take these structures and, as a first approximation, model them as single degree of freedom systems. And we can also model them as multi-degree of freedom systems, and We'll do examples of both in upcoming units. We talked about the natural frequency then is 1 over 2 pi times the square root of stiffness k over mass m, and typically represented in unit of hertz. And then the period is the inverse of the natural frequency. And of course, we're concerned about the possibility of resonance, where the frequency of the ground motion would be at or near the natural frequency of our structure, because then we can get that resonant response, and that can lead to failures of various kinds. Okay. Skip over a few slides that we saw last time. Now we're going to come back to this equation today, and we'll look at a specific waveform, and we'll evaluate it in terms of the Arias intensity. So we take the acceleration ground time history, square it, integrate with respect to time, multiply by pi, divide by 2g, called the Arias intensity. It has uses. It's actually represented in a velocity, although it's not velocity. It measures the units of velocity. The total energy content of the shaking is measured, and it's useful for landslides and soil failure assessments. Now, in the world of pyrotechnic shock, which I have more experience in, we have a similar parameter. It's called the energy parameter, and very similar to this, only we don't have the pi over 2g. And we talked about this Trifounet and Brady definition last time we met. Now, this is a new table that I put in to complement the Arias intensity. And this has got two columns, the intensity in meters per second or centimeters in second, and then showing then what kind of ground motion severity do we have for each of these intensity rows, and what the expected structural and geotechnical effects will be. So I'm not going to read through all those columns and rows, but you can take a look at that later. But here's what I will mention, is that later today we're going to take a look at the El Centro or Imperial Valley earthquake of 1940 in Southern California. And in the Arias intensity scale, it was 1.8 is where it was, so it would be in this row here, meters per second. So that is severe shaking, and that causes the collapse of weak masonry structures and major structural damage. In fact, we'll take a look at a couple of photographs of the damage that occurs. So yeah, we'll take a look at that here in a number of slides, maybe a dozen or so slides from now. New Madrid earthquakes. Okay, now we're starting into our new slide. So that was a review plus some additions. So I mentioned earlier this series of earthquakes. There's actually 3 of them, major earthquakes, 1811 to 1812, and this is along the Mississippi River. So the Mississippi River, and then we have what's called the Boot Heel section of Missouri, right here, and then Memphis, Tennessee, and this is this fault zone. So a series of very large earthquakes occurred between December 1811 and February 1812 in the central United States near New Madrid, Missouri. Estimated magnitudes, there was no instrumentation available at the time, but the estimated magnitudes were moment magnitudes 7 to 7.5. Now that's not the largest recorded earthquake that's happened in modern U.S. history, but it's up there maybe in about the top 3 or 4 or so. The earthquake occurred, the series, within the New Madrid seismic zone. Now this was not a tectonic plate boundary, but there was nevertheless a fault line, and it was buried underneath the ground in this we call the Mississippi Valley. Shaking was felt across most of eastern North America, reportedly ringing church bells in cities as far away as Boston. How about that? So, I mean, church bells are set to ring on certain special occasions, maybe certain times of the day, and so forth. But if you hear a church bell ringing at some odd time when it's not supposed to be, well, could be an earthquake is happening somewhere. Okay, the earthquakes caused extensive ground deformation, including surface faulting. Now, sand blows, there's sand volcanoes, there's soil liquefaction. And we're going to take a look at that in more detail in a couple of slides. But that has to do with there's an underground water table, and that water can get drawn up through fissures and porosity and come to the surface. And it doesn't turn the surface into liquid, but it kind of turns the surface into this kind of this mushy material, which we'll see the consequences of that in an upcoming slide for a different earthquake. Landslides, yes, those can happen. Now, I've heard it said that water does not flow uphill, and that's not actually true. It can under certain circumstances. So parts of the Mississippi River reportedly flowed backwards temporarily due to strong ground uplift and seismic waves. Really interesting. Now, at the time, that area was sparsely populated, which is a good thing, because now there's probably, in that fault area, if we close the whole area, probably 1.5 million people, something like that. And if this set of earthquakes were happened again, well, let's just hope and pray that our building codes are up to the task, and the quality and design and manufacturing of our buildings would be able to withstand this. We sure hope so. So this is just sort of an artist sketch print showing that, yeah, at the time, people lived in log cabins. That was the standard design of the homes in that area of Missouri and at that time period. And there was just all sorts of damage, and other things were happening too, like people were hearing these strange sonic boom type effects and thunderstorms. Just a lot of things were going on. So lessons learned. We like to figure out what is the lessons we've learned from that earthquake, because this will help us prepare for the next one. So this is called an intraplate. That's the key word, intraplate. Earthquakes can be very large. Major earthquakes are not limited to tectonic plate boundaries. The New Madrid seismic zone shows that ancient faults within continental interiors can still be active. So where we might be on planet Earth, earthquakes can happen. Now, in some parts of the world, earthquakes are almost non-existent, but I'm going to say earthquakes can happen anywhere. Seismic waves travel very efficiently in eastern North America. In the older, colder crust of eastern North America, that's very efficient for transmitting seismic waves with less attenuation that happens in the western U.S. So we mentioned again that this earthquake, New Madrid, the series was felt over a wide area, even all the way up to Boston. And soil liquefaction, we've started to talk about it a little bit. We're going to talk about it more. It can occur in river valleys, that's intuitively clear. Sand blows, lateral spreading, and ground settlement occurred in the floodplain, mentioned that. Saturated alluvial soils were particularly susceptible. A little footnote here, let's go back. So I keep talking about New Madrid earthquakes and Mississippi River. Well, as I make this recording, my wife and I are living near Huntsville, Alabama. So if that earthquake series would happen again, we would definitely feel it. May not have any structural damage, but that might shake our windows a bit and maybe knock some books off a bookshelf or that sort of minor damage. 1906 San Francisco. This was, in recorded history, modern history that is, of the United States, the worst case earthquake for death toll and damage. So early in the morning, April 18th, 1906, rupture along the San Andreas Fault. The duration of severe shaking was about 40 seconds. Now, high magnitudes and long durations go together. I'm not going to try and figure out here whether the one causes the other. Let's just say they correlate together. And references give the magnitude ranging from 7.7 to 8.25. Well, I got some good news and bad news for instrumentation. There was some operating instrumentation in place at the time of this earthquake. So there was equipment, seismographs running 24/7, 365 days a year. But the earthquake was so severe that the readings went off scale and the data was no good. Well, lessons learned. Yeah, lessons learned. Many people died, some due to the direct earthquake effects, but what we find with earthquakes and natural disasters of this sort is that it's secondary effects that can cause, in some cases, the majority of the deaths, particularly if there's a tsunami generated, for example. And in this case, there were fires that happened because there was ruptured underground gas lines. So there was natural gas being delivered to homes and businesses for heating and cooking and so forth, and those lines ruptured and there were sparks and ignitions, flames, fires, and the firefighters were unable to fight the fires because the underwater water lines for the fire hydrants, those were broken up as well, no water pressure. So then the people just had to let the fires burn out. And death toll estimates, these are all over the map, from 700 to 3,000 souls perished in that earthquake. Here you can see also from 1906 San Francisco, the smoke, billowing smoke in the background. So some lessons learned. This confirmed the elastic rebound theory of earthquakes. So what's that? So it's a theory explaining how earthquakes occur due to the sudden release of stored energy, stored elastic strain energy in the Earth's crust. Demonstrated surface fault rupture hazards, soil amplification. Now soil amplification is a big deal. We'll have a whole unit on structure-soil interaction in a future class, and we've already talked about the wise man builds his house upon the rock, bedrock, because bedrock tends to not or have very little amplification of ground motion, whereas loose sandy soil can cause a tremendous amount of amplification. And then the earthquake, another lesson learned, showed the weakness of unreinforced masonry buildings, highlighted the risk of post-earthquake fires. We can also have landslides and tsunamis and other secondary effects. Demonstrated the vulnerability of lifeline structures such as the water lines, for example. And this led to the development of modern seismic engineering and building codes. So every time a major earthquake happens, then it's time to revisit the codes to see if improvements are needed. Okay, here is the Santa Rosa City Hall. So this is some suburb of San Francisco, and you can see the top part of that City Hall, it just toppled over. So more lessons learned. Long structures, so tall structures, tall buildings, bridges and so forth, experience large displacements. Engineers observed that long, flexible structure, damage distortion, long bridges, pipelines, tall, flexible steel frame structures. So there's the word demand is used in seismic engineering. I don't think we use that much in mechanical engineering and aerospace, but there's this displacement demand. So is the displacement from the earthquake, is that within the limits of what the building can withstand? And the idea of displacement and story drift and so forth became central in response spectrum design. So in the aerospace mechanical engineering world that I mostly come from, we do a lot with shock response spectrum. And in earthquake engineering, it's simply called response spectrum. Got a little bit of different emphasis, but the basic concept is the same. It's based, for example, if you have a single degree of freedom system subjected to a base excitation, and you count for the base excitation time history and the natural frequency of the system and its damping, and then you calculate what the response will be, and that response can be acceleration or relative displacement, for example. Structures with, we'll do some of that later on. Structures with long natural periods can undergo large displacement demands, even if the accelerations are moderate. Okay, we mentioned El Centro, so now here's our El Centro slide. Imperial Valley, Southern California, 1940. Sad to say there were 9 fatalities, and the magnitude 7.1. In Imperial, 80% of the buildings were damaged to some degree. In the business district of Brawley, all structures were damaged, and about 50% had to be condemned. This caused 40 miles of surface faulting on the Imperial Fault, part of the San Andreas system. So you hear about the main faults, like San Andreas, for example. It's very common to have smaller branch faults that then are nearby. And yeah, the Imperial Fault is one of those branch faults from the San Andreas system. Total damage, I'm pretty sure these are $1940, was $6 million. So today, maybe, I don't know, a couple $100 million. Well, here's El Centro again. You see that house has suffered some damage. So before 1940, okay, yeah, we're going to talk about how do you actually analyze a structure then for an earthquake. So the traditional method has been used to use a quasi-static lateral force, and that is still used today. We'll talk about the American Society of Civil Engineers, their ASCE, and they have some methods, criteria based on quasi-static lateral forces. But that same standard also addresses dynamic analysis and dynamic response to dynamic forces. And El Centro showed us that earthquake forces are dynamic and time dependent. Structural response depends on natural frequency and damping. Very much so. Resonance can greatly amplify motion. So we can have, the ground itself can amplify motion if it's like a loose sand, for example, or soil liquefaction. And then the structure itself can have its natural frequency and cause further amplification, especially if the natural frequency of the structure is at or near than the predominant frequency of the ground motion. So this resulted in the development of response spectrum analysis, and we're going to do some of that, not today, but in a future class. Yes, we will. Modal analysis, time history analysis, we'll do all of those three. Many brittle structural elements failed. So in earthquake engineering, it's highly desirable to use ductile materials, especially ductile steels, and we want materials that can bend without breaking. And we realize that if we have plastic deformation, then for our steel beams and columns, that building may need to be condemned, but as long as we can then get the people out safely, then okay, we'll just demolish the building later on. It's the preservation of life. Well, hospitals are going to have a stricter requirement because hospitals have to be up and running during and after the earthquake. So we'll talk about special requirements for hospitals later on. They have more rigorous requirements. This insight contributed to modern seismic design principles such as energy dissipation, ductile detailing, and capacity design. And all of those topics to be covered in future classes. Now I've got a fun exercise. So I've got screenshots of the MATLAB GUI package. And then you can download that GUI package. There's a version if you have MATLAB installed on your computer. There's also a standalone executable version if you do not have MATLAB installed on your computer. So this is 12.4, and I'll just show you the still screenshots of how to do this screen capture. So you would go into the top tab row over to import data. There it is. Then you go down to library, and then over and down to seismic, and then time history. And I actually have the El Centro earthquake north-south data that we can take a look at. We also have east-west, and up means vertical. And of those three orthogonal components, the north-south horizontal to the ground was the most dramatic. And it is the most famous earthquake time history. It's still used today for different modal transient analyses and so forth. So here's what it looks like. Acceleration g versus time in seconds. Now that peak was about 0.35 g's. Let me get that right, g's. And so that 0.35 g's is called the PGA, the peak ground acceleration. And then this is very much low frequency energy, and it persists for about 54 seconds. Now we can do some post-processing on this. In fact, in a future class, we'll do a shock response spectrum, or what the earthquake engineers would something called a response spectrum. We'll do that later on. But right for now, let's go to Structural Dynamics tab, and then go over to the Seismic tab. And we're going to do something called temporal moments. Now I'm taking some temporal moment metrics from mechanical engineering and pyrotechnic shock and combining them with some from earthquake engineering, the shock analysis, because there's some overlap in the concepts. So then we should go over to the temporal moments, and you see the El Centro underscore NS. So the way you do that is then you click analyze, and then that takes its temporal moments. And you should see El Centro underscore north-south waiting for you. And then sometimes you might need to click on update list to see it. If you maybe you already had this open and then you called in El Centro, you need to click on update list. Let's put the time shift at 0. And then in mechanical engineering, we've got this energy parameter that is G squared seconds. And then we have a few others. Now, then we have the peak ground acceleration, which could be from pyrotechnic. Well, pyrotechnic has a similar concept. You just take the peak, absolute peak in the time domain. Here I call it seismic PGA. And yeah, it's about 0.35 Gs, as we mentioned. Now, earlier we talked about the seismic Arias intensity, IA, and that is going to be 1.812 meters per second. So energy and seismic Arias intensity are very similar concepts. And a whole bunch of slides ago, we saw that there is a row in our table from 1 to 2, and this fits within that row and closer to 2. And yes, there was severe damage and ground shaking that occurred, and you've seen the photographs already of that. And then there's the Trifunac-Brady duration, and I'm not completely sure what to do with that, but it is of some importance. Probably more for like landslide triggering and so forth. It turns out to be for El Centro north-south, 24.44 seconds. Okay, next up is the very famous 1964 Prince William Sound, Alaska earthquake, also known as the Good Friday earthquake. Happened March 27th, 1964 in the evening times. Now this has the distinction of being the largest earthquake ever recorded in North America. Not that it was the largest that ever occurred in North America, but it was the largest recorded, so in modern times, let's say. And the duration was rather long, from 3 to 5 minutes. So again, magnitude has a correlation with duration. Bruce Bolt lists it at 8.6 ms, where ms is the surface wave magnitude. And the U.S. Geological Survey gives it a 9.2 MW, which is the moment magnitude. So again, we got different magnitude scales. The MW, the moment magnitude, again, is the more commonly used. So the death toll was 131, and that was mostly due to the tsunami effect that happened thereafter. So on the left is a downtown Anchorage street, and you can see it's like a sinkhole effect that happened there. Now on the right is a J.C. Penney's apartment, on the right is a J.C. Penney's department store building, which was very badly damaged from that earthquake. Well, there's other effects too, so this is pretty interesting. So you might have studied like Euler column buckling at some point in your engineering education, and the long slender columns. Well, I'm going to argue that the longest, slenderest column that you could have would be railroad tracks. Railroad tracks can go for miles and miles. Yeah, I know they have little curves and bends and so forth. But the bends you see there were not part of the initial design, because the earthquake was so severe, this 1964 Alaskan, that those rails were torn from the ties, and then under the compressive loading, they buckled. So that is a very, very interesting way to demonstrate Euler column buckling in the real world, in this case, caused by an earthquake, 1964. Loma Prieta. Oh, yeah, we'll spend a whole bunch of slides on this. Makes a really good case history. 1989, San Francisco Bay Area. This had a moment magnitude of 6.9. Tragically, 63 people lost their lives. And the epicenter was in the nearby Santa Cruz Mountains. And this was a double-deck on-ramp to what's called the Bay Bridge. So there's several bridges that crisscross the San Francisco Bay. This is not the on-ramp to the Golden Gate Bridge. That's a different place. This is to the Bay Bridge. And this is particularly called the Cypress Street Viaduct in the Oakland. 2 traffic decks supported by reinforced concrete frames. The upper deck collapsed onto the lower deck. Now we're going to talk about soil conditions. Soil conditions are a big deal. So if you've ever flown around San Francisco Bay and you look down, there's certain parts of the bay that are kind of look marshy, for example. And what developers have done is they've gone in and they've taken gravel and rock and tried to fill in the marshland to make usable land for warehouses and other buildings. But the soil is still kind of weak soil, and that can be a problem for when an earthquake happens. So the structure, that viaduct, was founded on what's called soft bay mud, and that bay mud amplified the shaking, and long period components of motion increased displacement demand, and many columns failed in brittle shear rather than ductile flexure. So we like materials that can bend without breaking, that are very ductile, and brittle materials can just have sudden fractures. So here's a little more background on this. So soft soils have low shear wave velocity. We talked about that earlier today. And they have low stiffness, low strength, and longer natural periods. So when seismic waves enter soft soil, the wave velocity decreases, and then the amplitude increases. Now that's somewhat by way of analogy like the tsunami waves coming into the shorelines. Energy conservation requires that the amplitude, now amplitude can be acceleration, velocity, displacement, take your pick. So then the amplitude of each one of those 3 metrics, or each of them, is inversely proportional to the shear wave velocity. So the slower the shear wave velocity, the higher the amplitude will be. And then we can have ground acceleration and displacement amplified or significantly amplified. The motion duration increases as well. And this implies wave motion amplitude at the ground surface, which we certainly have, or can have, and did have in the case of 1989 Loma Prieta earthquake. So for this so-called soft bay mud, the low shear velocity, the low shear wave velocity is around maybe 100 to 200 meters per second. And that's much lower than rock and bedrock, which is upwards of 800 to 1500 meters per second. So we would much prefer the bedrock for a whole series of reasons, one of which is that then that wave propagates through much faster, and then that's going to be reducing the amplitude of acceleration, velocity, and displacement. So also bedrock does not tend to amplify the motion, but then soft sand, loose soil, soft bay mud does amplify the ground motion. All of those concepts are overlapping and run together, by the way. Now, this is a graphic I got. It's a really nice graphic, but I struggle with it a bit, and I'm going to tell you why I struggle with it a bit. But it will emphasize an important concept. So here again is the Cypress Viaduct, where the pancake type effect happened. We've got some failures of those columns. We'll talk more about that on the next slide or two. Okay, so here's the Bay Bridge, okay, and this is then the Cypress Viaduct leading up to that Bay Bridge. And then we have this light grayish dull pink is the soft mud. And then we've got this yellow is more kind of what we call sand and gravel. And this kind of orange is the bedrock. And then this is showing the acceleration waveforms of each of the 3. All right, now Here's why I really struggle with this, and I had to work with ChatGPT. Is those red waveforms? Those are not to scale any scale. In fact, they have independent scale factors. So those are not representing the true amplitudes like I wish that they did. But yeah, so time histories are independently scaled for visual comparison of frequency content and duration. Relative peak amplitudes do not represent actual PGA peak ground acceleration values. Oh, well. If I was plotting that, I'd make sure they had the G levels, all uniform scale, and so forth. So soft bay mud deposits had natural periods. So soft bay mud, this is this kind of dull pink color here, 1 to 2 seconds. Now the elevated freeway structure, that viaduct, had a similar fundamental period, which created a resonance. We can say then the period of the soil was close to the period of the structure. Alternatively, and equivalently, you could say that the dominant frequency in the soil was about equal to the natural frequency of the structure. And either way you look at that, that creates a resonant response with all sorts of dynamic amplification, both on the ground and throughout the structure. That creates a large displacement demand and increased column curvature demand, and a shear critical behavior was triggered, particularly in those columns. Now, compared to the nearby rock sites, the rock sites actually had a higher peak ground acceleration, but a lower displacement, and the bay mud had a much larger displacement, but a much lower acceleration. For the base input to whatever structures would have been at those locations. So more lessons learned, lower Prieta. The columns were built prior to modern ductile seismic detailing requirements. So yes, as we go along, we're just making it up as we go along. We have lessons learned, and each time there's a major earthquake, it's time to revisit the codes and see what we need to improve them. The columns had limited shear capacity and limited plastic rotation capacity. And here's a simplified, but I think a really nice summary of what happened. So there's amplified ground motion due to soft bay mud, which caused a high lateral shear demand. Diagonal shear cracking formed in the columns. Shear reinforcement yields or fractures. Axial load cannot be maintained. Upper deck drops onto lower deck. So there is a need for capacity design, and we'll be talking quite a bit off and on about strong column, weak beam philosophy. So the idea is our columns need to be kept strong to then carry the weight of the building and its contents, and even under earthquake loading. But the horizontal cross beams, then, we like those to be more on the plastic side with some what we'll talk about plastic hinges, and will allow for some plastic deformation in terms of the horizontal connecting beams. So strong column, weak beam, SCWB, is a seismic design principle used in moment resisting frames to control where inelastic behavior occurs. So that's the key, is we're gonna throw up our hands and say, yes, we know some plastic deformation is going to occur, but let's control where it occurs to do the least possible damage to the building. So we have something called ductile flexural hinges for these beams, and in terms of their nearby their connections with the columns. Now, hinge does not mean like a door hinge. It's not that kind of hinge, but we'll talk more about those details later on. And we want to prevent the columns from failing, especially in the brittle modes. So on the next slide, then we have reinforced column failure modes. Now this is just generic, and this is showing 3 different ways these reinforced concrete columns can fail. But I don't know that it has to be one or the other. I think it's possible that you could have combined effects, although these images go nicely with the 3 ideals. So we've got a buckling failure mode for reinforced columns. We have this kind of bulge, this compression form that can happen, compression failure. And then we have the shear failure. So the For the columns for the Cypress Viaduct, then this was the failure mode that many of them underwent or had. So it's along what's called the maximum shear plane, which is going to be at a 45-degree angle relative to this vertical surface. So that's the sort of effect that can happen, and we're familiar with this from metal fatigue as well. Slide. This will be our last slide for today, and then we'll finish the remaining slides on our next time we meet together. So this is a 1994 Northridge quake in California, Los Angeles area. Very early, 4:30 a.m. in the morning, January 17th, 1994. Had a 6.9 moment magnitude. Duration was about 20 seconds. Now this earthquake had the distinction in the United States of being the highest measured peak ground acceleration at 1.7 Gs. Okay, the key word there is measured, because the peak ground acceleration depends greatly on local soil conditions, and of course we do have some accelerometers, some seismometers at various key locations, but we don't have 100% coverage, so maybe some other point at a higher G level, but that's the highest we know of that happened ever for recorded earthquake history in the United States. Sadly, 57 precious souls died. The earthquake occurred along a previous unknown blind thrust fault. It's close to the San Andreas fault. Now, blind. So that was, remember we talked about New Madrid, a buried fault? Well, this was blind fault, buried fault. Those are similar, if not the same concepts. And the U.S. Geological Survey did not know about that blind thrust fault. The city planners, the emergency officials, first responders, no one knew about this fault even existed except for a couple of groups of people. See, as it turns out, at one time back maybe 1920, 1930 era, that the Los Angeles basin was a very prolific source of oil production. Well, there's a few oil wells left, but most of the oil that can be extracted has been extracted. At least, I mean, deep down there's more oil, but only a small amount of oil production is continuing in Los Angeles today. Now, what the oil companies do is they have a series of tests they can do, like set off a train of explosives along the ground and use geophones to measure the responses, for example, and they can detect whether there's an underground cavity. And, well, if there's a cavity, that could be a pocket of oil. Well, the oil companies, highly competitive, that they just held on to that knowledge from the measurements because, that's proprietary knowledge. This is a very economically competitive, and this is the company paid for it. It's our company's data. It doesn't belong to anyone else. Well, I think that was very short-sighted because for the ethics and morality, I'm not talking dollars. I'm talking ethics and morality. The oil companies should have disclosed that to U.S. Geological Survey. So then the U.S. Geological Survey could have passed that on, and the city planners, the emergency services would have been at least aware that there was this fault and that someday that might be the epicenter for an earthquake. Let's talk about epicenter. So epicenter is the point on the ground surface below which the earthquake happens. The hypocenter is where the earthquake really happens, and that's reference to the latitude and longitude of the epicenter, but then the hypocenter then includes a depth parameter as well. So all companies knew about this, but did not publicly disclose that, and they really should have. Yeah, I'm very passionate that you should. Yeah, I know. We all have bills to pay, but we really, as a society, really ought to do a better job of sharing knowledge. All right, well, thanks for coming. We're going to have some more fun next time we meet. We'll talk about an earthquake in Virginia that caused a crack in the Washington Monument. We'll talk about a couple of Japanese earthquakes that happened. Japan has had a whole series of notable earthquakes. We'll talk about two of them in particular. We'll talk about the worst case ever earthquake in terms of magnitude was 1960 Chile, and caused a tsunami that went all across the Pacific Ocean and even caused damage in Japan. We'll talk about that, and we're talking earlier about soil liquefaction, and these sand volcanoes are also called sand blows that can happen, and how we can just get this moisture coming up and get that wet, sandy, and silt layers and so forth, and how that creates an unstable foundation for buildings. We'll talk about, here's the soil liquefaction. Look what can happen is that the whole apartment building can topple over. That's what did happen in Japan in one of its earthquakes over there. And more fun topics to come. So thanks for coming today. Have a great rest of your day until we see you again, and bye for now.